When we picture our ancient ancestors, we usually imagine basic stone tools and simple shelters, yet scattered across the globe are megaliths built from stones so heavy that moving them stretches the limits of human imagination. For decades, these structures have posed a logistical puzzle. The people who built them had no combustion engines, no structural steel, and in many cases, not even the wheel. These 10 sites are currently at the center of a debate between long-standing mythology and the mechanical evidence being uncovered by modern research. Investigating these locations offers a look into how early societies developed the engineering methods used to build the ancient world. We begin at number 10, Stonehenge. Its central sarsen stones weigh up to 40 tons, while the smaller blue stones were quarried in the Preseli Hills of Wales, 140 miles from the Salisbury Plain site. While some theorized that glaciers deposited these stones, recent analysis of zircon crystals in local river sands found no mineral signature to support that idea. Human labor achieved the transport instead, likely utilizing massive sledge networks, greased slipways, and coastal rafts to move thousands of tons of rock across the island. At number 9, we find a different logistical puzzle in Micronesia. At Nan Madol, builders constructed a 30-hectare city on top of a coral reef using roughly 750,000 tons of naturally occurring basalt columns. By stacking alternating horizontal layers of these hexagonal logs, they created interlocking joints that stabilized walls up to 25 feet high without mortar. To maneuver basalt logs weighing up to 50 tons, the builders likely synchronized their efforts with the tides, using high water buoyancy to float the megaliths into position. Curious for these societies, raw weight and distance were logistical equations solved through centralized planning and collective effort. At number 8 is the 16th century Veerabhadra Temple in Lepakshi, India. The site is famous for its hanging pillar, which appears to be suspended above the ground among 70 intricately carved stone pillars in the hall. This massive block of granite does not fully touch the floor. Visitors often pass objects entirely beneath its base. The pillar is supported by its connection to the ceiling and a precise distribution of weight through the temple's overall structural frame. These anomalies provide evidence of a sophisticated understanding of load-bearing physics and structural engineering in the ancient world. At number 7, we arrive at the Moai of Easter Island. For years, researchers debated how the islanders moved nearly 900 statues from their quarries to ceremonial platforms miles away. Studies show that the statue's D-shaped base and forward-leaning center of gravity allowed them to rock side to side. Teams could pivot the statues, making them walk in a zigzag motion. This use of kinetic engineering allowed the islanders to move 70-ton monoliths across rugged terrain with relatively small groups. Moving from surface engineering to subterranean survival, we reach number 6, Derinkuyu in Turkey. This underground city descends 18 levels through volcanic tuff and could house up to 20,000 people. Over 50 ventilation shafts ensured air reached the deepest levels. Many of these shafts also functioned as wells, providing a secure water supply during sieges. For defense, the city utilized massive rolling stone doors, half-ton circular slabs designed to be operated only from the inside, allowing residents to seal off sections instantly. We see a similar mastery of scale at number 5 with the Nazca Lines in Peru, and at number 4 with the Great Pyramids, whose internal chambers were designed to distribute millions of tons of vertical pressure. At number 3 is the underwater formation at Yonaguni, and at number 2 are the sealed vaults of Padmanabhaswamy Temple. These sites represent a frontier where current archaeological understanding has yet to reach a full consensus on their construction. While many ancient mechanics have been decoded, the ambition behind these projects suggests there are still engineering principles we have yet to fully grasp. That brings us to our number 1 anomaly, Göbekli Tepe in Turkey. Constructed around 9600 BCE, it is the oldest known example of monumental architecture. This complex was built thousands of years before the arrival of agriculture, pottery, or the wheel, using only stone tools. These groups quarried and decorated massive T-shaped monoliths, some weighing up to 10 tons, and arranged them in circular enclosures. The sheer effort required to build this site suggests that the need to organize and engineer such structures may have actually led humans to develop agriculture to sustain a massive workforce. Other legendary locations, such as the mythological Golden Lanka, hint that many more buried cities may still hold evidence of sophisticated ancient engineering. The history of these structures reflects a legacy of human ingenuity, a series of mechanical solutions that we are only beginning to fully understand.